All right, hello. Welcome to this week's weekly review. This week we're going to go ahead and cover sections 9.1, 9.2, and 9.3 out of your textbook. So for your first, for the first section to cover is section 9.1. And this one, of course, is going to be over just the introduction and some basic modeling with differential equations. So first off, let's go ahead and start by defining what a differential equation is. So a differential equation is essentially just an equation that contains an unknown function and one or more of its derivatives. So some examples for what these could look like could be like dy over dx is equal to 4x squared plus 3, 3x cubed plus 2 equals 4xy prime, or x cubed y is equal to d squared y over dx squared. Now, whenever we're talking about differential equations, one thing that we do sometimes need to keep in mind is going to be the order. So the order of differential equations is essentially is going to be the order of the differential equation is essentially going to be the order of the highest derivative. So for example, right here, we see we have a dy dx in this first one. So this one, the order would be 1. Our second one, once again, we have just a normal y prime. So that would also be 1. And then we have a d squared y over dx squared, signifying that's our second derivative. So that order would be 2. And if we had an equation that says something like y parentheses for x cubed y squared equals y double prime times the square root of x. This one, our highest order would be 4 because of this right here. So therefore, our highest order is 4. And just an important thing to know, this probably won't come up like a ton. If this number up here is in parentheses, that is signifying a derivative. If it's just plain like this, that's just a normal power. So that's just something to keep in mind as you go ahead and look at your differential equations. So let's go ahead and move on. So now that we've kind of talked about what an equation is, let's talk about what a solution is. So a function f is called a solution if the differential equation is satisfied when y equals f of x and its derivatives are substituted into the equation, into the equation. So essentially what this is saying is if you're given a differential equation and then you solve for that function, so for example, if we scroll back up, if we were able to solve for some y equals f of x up here, then everything would have to fit. So for example, right here, this y prime that we would solve for, that would have to make sure that everything in that equation fits. So for a quick example of just, all right, let me go ahead and actually define this real quick. So when we're talking about solutions, we have two types. We have general solutions, and these can also be called a family of solutions, and that essentially means that we are given some sort of function with a plus c. So we solve for our y equals f of x, and then whenever we do that, since we have a derivative, we would have to integrate to get rid of that derivative. So when we integrate, of course, we usually have an y equals f of x plus c. So a general means that we just have that c in there. We don't have anything to solve for it. It's just there. Whereas we can have particular solutions, and that essentially means that C is defined. So when we have a particular solution, essentially what they do is they give us a point somewhere on that equation, and they just say, like, solve for the equation, and you know it has to contain the point 1, 1. When you're done solving your equation, you plug in your point and then solve for C. Pretty similar to how we would with an integral. So now that we've cleared that up, let's go ahead and do a quick example. So what we want to do is show that y equals 2/3 e to the x plus e to the negative 2x is a solution to the differential equation y prime plus 2y is equal to 2e to the x. All right, so what we would have to do in this case is is that if we look at our differential equation, we already know once e to the 2x that's defined, we don't really need to worry about that. What we do need to worry about is that y prime and that y. So if we go back to our problem, we already have a definition for y, or at least one that they've given us to try to look at. So, but we also need to find our y prime. So in order to find our y prime, we just derive to get us y prime is equal, derivative of 2/3 e to the x is just 2/3 e to the x. Derivative of e to the negative 2x is going to be minus 2e to the negative 2x. So now that we have definitions for our y prime and our y, we can go ahead and plug those in. So we know y prime, we just said, is 2/3 e to the x minus 2e to the negative 2x plus 2 times y, so 2 times 2/3 e to the x plus e to the negative 2x is equal to 2e to the x. So now we can go ahead and try to play with this and see if we can get our left side of our equation to match the right. So we have 2/3 e to the x minus 2e to the negative 2x plus 4/3 e to the x plus 2e to the negative 2x equals 2e to the x. All right, so if we go ahead on here, let's go ahead and look and see if there's anything we can simplify. We have a negative 2e to the negative 2x and a positive 2e to the negative 2x, so we know those are going to cancel out. And then we have a 2/3 and a 4/3 e to the x, so if we add those together, we're going to get 6/3, which will go to 2e to the x equals 2e to the x. Therefore, we have verified that y equals 2/3 e to the x plus e to the negative 2x is a solution. So let's actually try another example. In this example, we want to know for what values of r does the function y equals e to the rx satisfy the differential equation 2y double prime plus y prime minus y equals 0. All right, so in this scenario, we don't exactly, we're given a y and we're given an equation, but we have to figure out part of that y. So, and they also give us, in our differential equation, we have a y prime and a y double prime, as well as our normal y. So our first step needs to be go ahead and take our first and second derivatives of our y. So we're going to get, if y equals e to the rx, y prime is going to be re to the rx, and then y double prime would be r squared e to the rx. So now that we have everything defined, we can go ahead and plug it in. So we're going to get 2r squared e to the rx plus re to the rx minus er e to the rx equals 0. So if we look at our equation in here, we can see that we have a common factor of e to the rx that we can go ahead and pull out. So we're going to get 2r squared plus r minus 1 equals 0. So if we look at this, we have one factor is our exponential. And one aspect of exponentials is that they will never touch 0. So therefore, we can't really do anything with that. But of course, we have our polynomial in here with our 2r squared plus r minus 1. So let's go ahead and try to factor that and see where that can equal 0. So if we can get a 2r and an r, we know since we have a 2r squared, and then we know we're going to have a minus 1 and a positive 1. So what we can do is we can go ahead, just factor it out. We can get a positive 1 right here, minus 1 right here. And we get 2r squared plus 2r minus r minus 1. So therefore, we're good. So therefore, in this case, we know that r would be equal to -1 and positive 1/2. So therefore, y equals e to the negative x, and y equals e to the x over 2 would be our solutions. All right, so now that we've done that, there's one other aspect that we can talk about. So now that we've kind of gone over just basic differential equations, there's one other pretty simple aspect to these. One little subset of differential equations are called initial value problems. And essentially, that's when they contain an initial condition usually in the form y of 0 equals some number, we'll just call it c, on f of x. And therefore, what you can do, or well, let me call that, I'm going to call that a, because we're going to call that, that gives us, it defines some like initial point on there. And therefore, you can solve for the plus c at the very end in your general equation, or for like a particular solution. So let's try an example with this. For this one, we want to solve our equation y prime is equal to 3e to the x plus x squared minus 4. And they tell us that our y of 0 is equal to 5. So let's go ahead and work on solving this. So we know that y prime, of course, is dy dx. Or better yet, we have dy dx is equal to 3e to the x plus x squared minus 4. We can actually kind of move that dx over to the other side. And then integrate both sides in order to solve this equation. So the integral of dy is going to be just y. And we integrate our right side of the equation like we normally would. So the integral of 3e to the x is 3e to the x. The integral of x squared is going to be 1/3 x cubed. Integral of 4 is going to be, of negative 4 is negative 4x, and then our plus c. But since they give us our initial value, we can actually go ahead and solve for c. So in our initial value, what this is essentially saying is that x is 0, when x is 0, y equals 5. So we can plug both of those into our general equation. So we have 5 equals 3e to the 0 plus 1/3 times 0 cubed minus 4 times 0 plus c. All right, so we have 3 times e to the 0 is 3 plus 0 plus c. Therefore, c is equal to 2. And our particular solution is going to be y is equal to 3e to the x plus 1/3 x cubed minus 4x plus 2. All right, so that's just been a little basic intro on differential equations. So now let's talk about what we can actually do with these. So one big thing that we can do with differential equations is going to be our population growth model. So when we think of population growth, one thing we can do is we can assume that population grows at a rate proportional to the size of the population. Or essentially what this is saying is when we have a small population, our population will probably grow at a small rate. But as the population grows, the rate at which it grows gets bigger as well. So when we think about this, we need two variables. We have time and, of course, population. So if we think about this as an actual equation, we know that we have the population grows at a rate. So our population growth rate could be defined as dp over dt grows at a rate proportional to the size of the population. So we can say we have some constant k times the actual size of our population. In this case, k is just a proportion constant. But what if we want to go ahead and solve for p? But what if we want to go ahead and actually solve for p itself in terms of t? Well, what we can actually do is we can go ahead and actually play with this equation. So if we look at this, we can see that our derivative is actually a multiple of itself. And we know that another function where its derivative is a multiple of itself is an exponential. So therefore, what we can do is that implies that our population growth will be some sort of exponential function. So we can hypothetically, for now, say that p of t is equal to some constant c times e to the kt. If we do that, we can say that dp over dt, we can also rewrite that as p of t, p prime, is equal to c times ke to the kt and this is coming from whenever we derive this piece up here, we have c times ke to the kt. And we know if we play with that a little bit, we can say that's also equal to c to k times ce to the kt, which brings us right back to saying that we have k times p of t, which brings us back to our initial formula. So therefore, we can for sure say that our p of t is equal to some proportion coefficient e to the kt. Yeah, some constant c times e to the kt. So now let's think about what this would actually look like graphically. Since we have no real definition for c or k, we can assume that it's going to be just some sort of general exponential, but we don't know exactly where. So it could look anything like this. But we also have to think about the fact that we're talking about population. And we can think of it, so population can never be a negative number, and even then if it's at 0, it's functionally, you can't grow from having nothing. So if we're talking about population growth, we have to assume that population, oh yeah, this is P and this is T right here. That population has to be greater than 0. And also, if we're thinking about time, it wouldn't really make sense for us to be using a negative time. So therefore, we can also assume that time also has to be greater than 0. So therefore, if we were just to graph this out, just to take a look, it would have to be something like this. So now let's talk about some properties of this model. So at t equals 0, we know we can say that p of 0 is equal to c e to the k of 0, which would simplify down to c. So therefore, C would actually be our initial population. And we also have to think about this as an essentially ideal model. Because in this scenario, there's no factors that would limit the growth of a population. It can just grow and grow and grow and grow and grow with nothing to stop it. But in a real life scenario, there would be factors to stop population growth, competition for food and shelter and things like that. You can't just kind of keep growing at an exponential rate and expect things to just kind of just infinitely grow. We have because there's a limit of resources. So that brings us to the logistic model, or also known as a logistic differential equation. Now, this kind of goes off of our initial idea that population grows exponentially, but it will level off at some carrying capacity m that we'll call m. So essentially, if we think about this practically, as resources become more scarce, it would make sense that the growth rate would start to slow down as we start hitting that peak amount that we could actually hypothetically keep track of. And if we think about this, is that if we have a population that gets bigger than our carrying capacity, that's going to have, our population will have to shrink in order for resources and everything like that to maintain itself. So therefore, P may decrease if population is greater than our carrying capacity. So now, based off of this, mathematically, what we can say is that our initial model, that our ideal model can work, or at least be very similar, as long as our population is small enough. And we also know that if we get above our carrying capacity, that our population has to decrease, therefore our growth rate would be negative. So what we can do, there's a way you can combine these equations to get us our actual new model. And this one states that our dp over dt is equal to kp times 1 minus P over N. And some other fun and some other interesting aspects of this is that in here we have what are called equilibrium solutions. And an equilibrium solution is going to be whenever our rate levels off to 0. So essentially at that point it means our population is neither growing nor shrinking, it's just staying at a constant equilibrium rate. And another interesting aspect of this is that as our population approaches our carrying capacity, our growth rate will approach 0. So if I show this graphically, let's say we have our carrying capacity up here. For no matter where we start, we're going to have to approach that carrying capacity at some point and it'll level off. So now let's go back to these equilibrium solutions. So if we think about this, there's going to be two places where we'll have equilibrium solutions. Our first one is going to be when P equals 0. So if we plug that into our logistic model, that's going to get us an answer of 0. And that also makes sense because if we have no population, then we can't grow anything. We can't grow something that doesn't exist. The other place where we will have an equilibrium solution is going to be when our population hits our carrying capacity. Once again, if you plug that into our equation, that's going to simplify out to get a 0. And also at that point, like we said, at that point, once we hit our carrying capacity, we can't grow anymore. That's going to have to level out in order for us to kind of maintain a population. So let's just do a quick example working with this. So for this one, we're given the logistic model. dP over dt is equal to 1.2 P times 1 minus P over 4,200. And we want to know, when is our population increasing? When is our population decreasing? And what are our equilibrium solutions? So we can first go ahead and start this off by essentially solving for our equilibrium solutions first. So I'm going to go ahead and just write down little answer slots right here. So we know that our equilibrium solutions, we are neither growing nor shrinking. So if we say that 0 is equal to 1.2 P times 1 minus P over 4,200, if we look at the factors, we know that is going to be when our population is 0 and when our population is at 4,200. Since if we plug in 0 right here, we're going to get 0. If we plug in 4200 right here, we're going to get 1 minus 1. So therefore 0. So now we have to think about when we're increasing and decreasing. So when our population is increasing, we know that dp over dt is greater than 0. When we're decreasing, it is less than 0. So if we're greater than 0, we can think back to how we went ahead and defined our growth rate, and we can also solve for it just for kicks. But we had essentially said that we have to be growing if we're in between 0 and 4200. We can graph this out, or we can go ahead and plug in numbers. Like, for example, we could plug in, for example, one thing we can do is we can treat this sort of similar to how we did increasing and decreasing back whenever we did back in 2413, how we defined whether a function was increasing or decreasing. So that's one way you can do that. Or you can just think back to our definitions of the logistic model. And we also know that we have to be decreasing if we are below 0. But I'm going to put that in a parentheses because I mean hypothetically that you can't really have a negative population. But you for sure have to decrease if you are above 4200. And like I said earlier, what we can do, we can either do negative infinity, 0, 0, 4200, 4200, and bigger, like we did with our increasing, decreasing. Plug a number in. If we plug in -1, we're going to get, if we plug in -1, we're going to get a negative times a positive. Therefore, we're decreasing between 0 and 4200. If we plug in 1, we're going to get a positive times a positive. Therefore, we're growing. If we plug in 4301, we're going to get, if we plug in 4300, we're going to get positive times negative. Therefore, we're decreasing then. So now let's go ahead and move on to slope fields. So slope fields, essentially how we can define these is that if we are given a differential equation which relates our first derivative, or dy dx, to x and y, the slope field for the differential equation is a graph of small portions of tangent lines a small portion of to possible solutions of various points. So essentially what this is saying is that if we have some sort of equation that says dy over dx is equal to some sort of x and y, some sort of x and some sort of y, doesn't really matter how they're organized. We can pick points. We can pick different x and y points, plug that in, get our slope, get our dy dx, and we can say that is the slope of the tangent line at that point and graph it. So, for example, just to kind of do a quick one about how to draw slope fields. And also slope fields can be called directional fields, just as a little note. What I like to do is I like to make a table, and so what we can do is we can pick a point, plug into your derivative, and then you can draw a short line where the slope of that at that point. So just to kind of show you an example with like a few points, let's say that we have, I'm just going to stick to the first quadrant for this example. And we're going to say we want to draw a slope field for y prime is equal to x minus y plus 1. So what I like to do is I like to go ahead and build a table. Let me just go ahead and just insert some points right here. I like to go ahead and build a table of, with one column being our point and our other column being our y prime. So therefore, let's go ahead and do a few points. Let's say we have 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, and 1, 2. So what we do is, so we have our, for our first point, we have our point 0, 0, which we would plug into our y prime. So in this case, it would be y prime would be equal to 0 minus 0 plus 1. So therefore, we have a 1 right there. We continue down the column, so we get 0 minus 1 plus 1, which is 0. 0 minus 2 plus 1, so negative 1. We get 1 minus 0 plus 1 is 2. 1 minus 1 plus 1 is 1. And then 1 minus 2 plus 1 is 0. So now that we have all of those defined, what we can do is we go over to those points. So we know, for example, at 0, 0, our slope is 1. So we just draw a little hatch mark with a slope of 1. At 1, 0, we know it's going to be 0. So we just go ahead and just draw a little level slope. Pretend that's level. At 0, negative 2, it's negative 1. So we're just going to draw a little slope down like that. At 1, 0, we know it's going to be 2, so we're going to draw a little bit steeper slope than our first one. 1, 1, it's going to be 1, and 1, 2, it's going to be 0. So what you can do, so one thing we can do with slope fields is we can actually go ahead and solve for solution curves. So what they may do is they may say, here's a slope field, draw the solution curve at this point. Now you can even just draw different solution curves based on what we have. Now it can be kind of tedious to do, so if you're doing everything by hand, you can go ahead and just draw stuff by following along. So for example, right here, we're just going to maybe do not all of these, but a couple. We have one that says sketch the solution curves for these points, and they give us some options. So what we want to do when we sketch solution curves is we kind of want to go along with the direction field. So we start off with our points. So for example, for A, they give us 0, 0. So we know we start off right here at the origin. And what we want to do is we kind of want to follow along with kind of the direction curve gradient. Kind of like that. They don't necessarily have to completely intersect, but you want them to kind of follow along. And we could do this again at 1/2, but 1/2, if we start here, we know we're just going to have a straight line. If we go over to 1, we just kind of, like I said, once again, you just kind of follow along with the gradient of the direction curve. It doesn't, like I said, doesn't necessarily have to intersect with some of those points because you don't know exactly, like, you may not know exactly which points are there on your graph, but they're kind of a good hint. And then lastly, we have our 1.6, so about right here. We're going to kind of go up and kind of get steeper as we go up. And then we can see right here, it also says find the equilibrium solutions. So like we said when we were talking about our population growth model, is that our equilibrium solutions are going to be points to where our derivative is going to be equal to 0. So in this case, equilibrium solutions are where dy dx is equal to 0. So if we look at this graph right here, we can see we have a couple points where that happens. We can see that no matter what, wherever we at y equals 1/2 and y equals 3/2, we can see that that just stays at 0. It doesn't change. So therefore, our equilibrium solutions would be y equals 1/2 and 3/2. So then lastly, let's go ahead and work on trying to match with slope curves. I mean with slope fields. So like we said earlier, now that we kind of know how to draw with them, let's kind of talk a little bit about matching with them. So I kind of like to work backwards with these. So for example, we have these 4 slope curves and we have 4 equations over here on the right. And we want to be able to match them with each one. So what I would do is I would go ahead, especially if you're trying to match, and make a table. And say have one for your xy, and then one for each of your 4 y primes. For each of your y primes. So we're going to do y prime A, y prime B, y prime C, and y prime D. So we can take different points and plug them in. So for example, let's start with 0, 0, and see what we have for each of these. So if we plug in 0, 0, and for A, we're going to get y prime equals 2 minus y, so we're going to get 2. For B, we're going to get y prime is equal to 0 times 2 minus 0, so 0. C, we're going to get x plus y minus 1, so 0 plus 0 minus 1. And then for D, we're going to get sine of x times sine of y, so therefore we're going to have 0 times 0. All right, so now let's go ahead and look and see what we have for each of these. So we can go ahead and look and see at 0, 0. So we have one where this is at 0, 0. We have this one. So 1 is going to be 0. 2 at the origin, it's not defined. But it could be 0, and that's an equilibrium solution. So that's another thing to keep in mind. Over here at 3, we can see at 0, 0, we have a positive slope, and we only have one of those, so we know that this one has to be A. And then lastly, at 4, we can see we have a -1 slope at 0, 0, so therefore this one is going to have to be C. So now what we need to do is we need to go ahead and distinguish between B and D. So let's go ahead and try moving over just a little bit. So let's go ahead and try zero and let's try 0 and pi over 3. So we know pi over 3, we're just going to approximate that to be 1, since 3.14 over 3. So we just care about B and D right now. So at B, we're going to get x equals 0 times 2 minus 1, 0. And then we can see at D, we have, well, that's still 0. That doesn't help us. Let's try pi over 3, pi over 3. Actually, you know what? Let's do pi over 6. That one's going to be a little easier to work with, I think. Let's try pi over 6, pi over 6. So we're going to approximate pi over 6 to be 1/2. So if we look at this, we can get, for B, pi over 6, we're going to get 1/2 times 2 minus 1/2. So 1/2 times 3/2. So we're going to say that's going to be about 3/4. And then D, we know sine of pi over 6 is going to be 1/2. So we're going to get 1/2 times 1/2, so that one's going to be 1/4. So in this case, what we can do is we can try to look at these and see which one's going to be more shallow. So if we go up here, we can see this is about, this is about right here is going to be 1/2, 1/2. And then over here, we can see and then that's about 1/2, 1/2. So this one over here, 1 looks a little steeper than it does at 2. So therefore, what we can do is we can say, so we can say that 1 is going to be B, and then 4 is going to, and then 2 is going to be D. All right, so now let's go ahead and look at separable equations. Let's move on to our next section. So our next section is going to be section 9.3, separable equations. So for separable equations, our definition for these is that they are going to be first order. So like we said earlier, first order, that means that the highest derivative we're going to have is just the first derivative. So it's going to be a first order differential equation in which dy dx can be factored as a function of x times a function of y. So rewriting this, it would essentially say that we have some sort of dy dx can be equal to f of x times g of y. But let's say hypothetically we wanted to be able, let's say hypothetically we wanted to play with this a little bit. So where we had f like x over y, some like our function of x over a function of y. What we can do is, as long as g of y does not equal 0, we can say that h of y is 1 over g of y. Therefore, dy over dx is equal to f of x times g of y. Now, if we have this format, we can actually work with this and say that we can actually rearrange this and say that we have, oh wait, this is h of y right here. Let me just rewrite that. F of x over h of y. We can now say that we have h of y dy is equal to g of x to f of x dx. And therefore, if we were to integrate both, and therefore we can integrate both sides and they would be equal to each other. So that's the basic setup for a separable differential equation. So when we're solving these, it's also important to note that in addition to general and particular solutions, we have other types of, we have another way to type solutions. We have explicit solutions, and that essentially means that we have a for sure y equals f of x as our solution. Implicit is anything that is not that. So think of it as maybe being something like g of y is equal to f of x. Like we can't fully get rid of everything on the y side. So for example, if we had, if you solved it and you got y cubed plus y equals x squared plus 3, we can factor out one y, yes, to get y squared plus 1, but we can't really do anything else. There's no way how we can get just y by itself. So therefore, we'd have to say stop here. Yeah, so therefore, we'd have to stop here and say that that is going to be our implicit solution. So now let's go ahead and just do a couple of examples of these. So for our first example, we're going to say that we have dy over dx is equal to x square root of y. So our first step when we solve differential equations is that we want to essentially get all the y's on one side and all the x's on the other side. So what we can do is we can go ahead and multiply times 1 over square root of y on both sides. And then move the dx over to get us 1 over square root of y dy is equal to x dx. I'm going to personally rewrite that as y to the negative 1/2 just to make that easier to integrate. So therefore, we're in the right spot. We have our x's and our y's all on the same side together. So now we need to go ahead and integrate both sides. So if we go ahead and integrate both sides, we're going to get integrate y to the negative 1/2 is going to be 2y to the 1/2 plus c is equal, if we integrate x, it's just going to be 1/2 x squared plus c, and that's where we stop so far. Now what we can do is we can actually go ahead, combine these c's, and just make a new plus c. So 2y to the 1/2 is equal to 1/2 x squared plus c. And now we can go ahead and solve for y. So we can divide both sides by 2. So they can get y to the 1/2 is equal to 1/4 x squared plus c. And then we can square both sides to get us y is equal to 1/4 x squared plus c all squared. And since they didn't give us any point, we're just going to have to stick with our general solution. So let's try another one. In this one, we have dy over dx is equal to x e to the y. And they also tell us that y of 0 is equal to 0. So let's go ahead and solve this like we did earlier. Our first step is going to be to go ahead and get our x's and y's on both sides. So move the dx, move the dy, and then divide by e to the y to get us e to the negative y dy is equal to x dx. We can go ahead and integrate both sides. So e to the negative y, if we integrate that, we're going to get negative e to the negative y plus c is equal to 1/2 x squared plus c. Of course, we can move our c over, so we're going to get negative e to the negative y is equal to 1/2 x squared plus c. So now let's go ahead. We can go ahead and get rid of that negative while we're at it. So e to the negative y is equal to negative 1/2 x squared plus c. So now we have this exponential that we need to get rid of. So now we have to go ahead and figure out how to get rid of this exponential. So if we think back to our properties, we know that the natural log of e to the x is equal to just x, because of course the natural log and the e will cancel out. So we can take the natural log of both sides, So we can get negative y is equal to the natural log of negative 1/2 x squared plus c. And then, of course, multiply both sides by -1 to get us y equals natural log of negative natural log of negative 1/2 x squared plus c. But of course, this time, remember, they gave us our initial condition. So therefore, we need to go ahead and solve for c. So we have 0 is equal to the negative natural log of negative 1/2 times 0 plus c. All right, so we get 0 is equal to the natural log of 0 plus c. We know the natural log of 1 is 0, so therefore c is 1. So our final solution would be y is equal to the negative natural log of 1 minus 1/2 x squared. So that is all I have for today. So hopefully you guys did well on your last exam, and good luck on any future assignments.